So this is actually the one that I laid out on the opening slides here. And missed a format here. So this is something called an isomerization reaction. Basically, these atoms are flipping. And supposing that it's first order, so it follows the equations that we just learned, that the concentration is 85% of its original value after 247 seconds. And that, believe it or not, is all you need to know to determine the rate. And then there's a second part of the question: at what time will the concentration of CH3NC be 25% of its original value? So let's just run through this, and I'm just going to show you the whole thing here. This is the first problem. So basically, the one thing that is useful in this is knowing how to deal with concentrations being talked about as percentages of the initial concentration. So all you need to do is, in this case, saying that it's 85% at a certain time, all that is saying is that A at t is equal to 0.85 of what it was initially. And that's exactly what I put in here, where the AT usually is. And from there on in, it's actually incredibly straightforward. The A0s cancel out. And so then you get this expression 0.85 equals e to the kt. And so use a natural log to get rid of the e. So you get natural log of 0.85 equals negative kt. And then it's just solving for the k. So divide both sides by negative t. And here, the natural log of a number less than 1 is negative. We have a negative sign here. This is going to be a positive result. Rate constants need to be positive, and that clocks in at, once you actually punch the numbers in, you get 6.58 times 10 to the negative 4 inverse seconds. So that was the first question. And getting that was, you needed that rate constant to actually get the second part of the question. At what time, I realized I forgot to write the word time, so we'll do that. And here is that one. It popped up. And again, same setup, 25%. So know that A of t is just equal to 0.25 times A0. It's the almost exact same algebra, except in this case we are solving for t and not k. And that gives us, in the end, about 2100 seconds, or 21 and 7 seconds. And again, make sure you are familiar enough with your calculator and the exponential and the natural log operators to be able to replicate these answers. One more thing. A question that is often asked, this comes up with radiochemistry a lot, so dealing with radioactive things. How long will it take for the concentration of something, we'll just keep calling this A, to drop to a half of its original value? And this is a good chunk of the group activity for when we actually meet face to face. So we're just going to work through it because it's an interesting result. Now this time, which is often used as a way to describe a rate constant. Instead of a rate constant, sometimes this value is given. Now this time is called, surprisingly enough, a half-life, or T1/2. So how would you go about figuring this out? So let's go back to our cyclo kind of triangulopropane. So we had the basic first order kinetics rule. Cp at time t is equal to Cp at time 0 equal to negative t. And we're going to do almost the same substitution that we did before. And what we can say is that, at the half-life, this is just equal to 0.5 times Cp. at time 0. And we're just going to substitute that in, like so. And from here on in, it's pretty straightforward. The CP at time 0 terms cancel out. So you get 0.5 equals e to the negative kt. And the natural log is equal to, the natural log of 0.5 time is equal to negative kt, which means that this half-life, the time that it takes to go from, whatever concentration, half of that, is equal to the natural log of 0.5 over k. Now, the natural log of 0.5 is a number, it's a constant, and so is k, and so that means that it's going to be equal to in this case, the natural log of 0.5 is equal to negative 0.693, so that's why this negative sign went away. 0.693 and then divided by the rate constant, which gives us a total of 1,034 seconds. Now, think about what that means. That answer, once we got to here, there was no variable in there. There's no concentration. It is just a constant. And for this particular reaction, it is equal to this constant. For another reaction, it will be a different constant because the rate constant is going to be different. But the important thing is that for first order kinetics, that half-life is always the same. It doesn't matter what the starting concentration is. Now think about that. What I'm saying here is to go from 1 molar to half molar, it would take 1,034 seconds. But to go from a half molar to a quarter molar also would take 1,034 seconds. To go from 0.25 molar to 0.125 molar also would take 1,034 seconds. So it doesn't matter what the starting concentration is. For this reaction, it will take 1,034 seconds for it to reduce by a factor of 2. And now, is that inconsistent with what I told you before? That these rates, now remember that the stuff we started talking about last time. Yeah, rate is equal to, at any point in time, the rate constant times the instantaneous concentration. And that concentration, though, is always going down. So if the rate is going down, shouldn't it take longer each time because the rate's slowing down as the concentrations go down? And the answer is there's two things going on. For each, as we go from one half-life to another, yes, the rate of the reaction is continuously dropping. But what is also dropping is how much reaction you need to go. So you have to only convert, for each successive half-life, you have to convert less and less stuff. And it turns out that for first order kinetics, those two factors exactly cancel each other out. And this, in fact, is one way to determine if a particular reaction follows first order kinetics, and that if the half-lives are a constant. I should note that for second or third order reactions, the math is very different. They're a little more complicated. You don't want to see them. That's something I subject the 1225 kids to. And that this, in fact, doesn't work out this cleanly. So they have a totally different set of equations that you need to use. But you guys just need to know the first order stuff. And technically, you now do. And we've just got 2 topics left, kinetics and acid-base stuff. All right, we will see you next time.